Hi there, Miss Heaton here. We're going to be talking today about Graham's law and Dalton's law. These are our last two gas laws. I'm sure you'll agree that is cause for celebration, and this is from chapter 13.6 in your book if you'd like to refer to that for future examples and information. So the first law we're talking about is Dalton's law. Dalton's law deals with a partial pressure of gas. And this occurs when you have several different gases mixed together. As you can see here, we have gas number 1 with a kind of a medium pressure, gas number 2 with a pretty low pressure, and gas number 3 with a higher pressure. When we mix all three of those together, we end up with the sum of all those pressures. The pressures are additive. But in this total mixture, each gas, the green gas, the blue gas, and the orange gas, exerts a partial pressure. And that's just the part of the total pressure that each gas contributes. Here's another example of where Dalton's law applies. We know that STP, standard pressure, is 700 millimeters of mercury, or 1 atmosphere. Well, why do we have that air pressure? Why is that the pressure of the atmosphere? Well, in air, you have all these different gases. Most people think that air is mostly oxygen. That's actually not true. It's about 80% nitrogen, along with some carbon dioxide that we breathed out, and a little bit of argon, an inert gas. Well, the pressure of 760 is caused by nitrogen, oxygen, argon, and carbon dioxide molecules hitting you, hitting the walls, hitting everything around it. And we could calculate based on the percentage what the partial pressure of each gas is at standard pressure. If you add up all these partial pressures, it adds up to the total atmospheric pressure. So kind of Dalton's law as applied to this situation is that the total air pressure or atmosphere pressure is the sum of all the partial pressures. And that's exactly what Dalton's law said. Here's the equation for Dalton's law. He said that the total pressure of a mixture of gases equals the sum of the partial pressures of each gas. And guys, it really is that simple. It's adding. So let's look at an example here. You have a flask of water vapor, H2O gas, at 0.32 atmospheres mixed with oxygen, O2, at 0.16 atmospheres. What is the total pressure? Okay, well the total pressure is the sum of each of the partial pressures. In this case there's just 2. So to get the total pressure, you would just add up 0.32 and 0.16, and you would end up with a total pressure of 0.48 atms. And that's all there is to it. The only way I can make that trickier is if I change the units on one of them. Here's another instance where Dalton's law comes into play in scuba diving. I don't know if you've ever been scuba diving. I haven't because I get anxious being underneath the water for that long. But if you've been scuba diving, you may know that you have to breathe out of an oxygen tank. Now, they don't just put pure oxygen in there. They put some nitrogen, well, air has mostly nitrogen in it, right? If you go to really high pressures way underneath the ocean, we know that at high pressures, as pressure increases, what happens to volume? It decreases, right? But then when you come back up to the surface, the opposite thing is happening. You're going to a much lower pressure than you were at when you're underneath the water, and so the volume of gas is going to increase. And what happens is when you're deep in the ocean, some of the gas that you're breathing in dissolves into your blood, especially if there's nitrogen in there. That dissolves very well in your blood, especially at high pressures. As you come back up to the surface, that pressure is going to decrease, so the volume increases, and you end up with these big bubbles of nitrogen that have grown inside your blood vessels. It's very uncomfortable, and it causes something called the bends, which if it's bad enough can be fatal. If you have any stories about this, I'm sure we'd love to hear them in class tomorrow. So what they do instead is, instead of putting nitrogen in with the oxygen, they put something like helium, an inert gas, which won't react with anything in your body, and it's small, it's very undense, and it won't dissolve in your blood as much, so that you won't have the same effect. When its volume increases slightly, it's still pretty small bubbles, and so it's not going to cause the bends. So the whole point here is that the oxygen in your tank contains maybe helium and oxygen. Okay, one final application of Dalton's law is if you are generating a gas. Let's say you're reacting something like potassium perchlorate. When you heat it, it will give off a gas. And if we wanted to collect that gas and see how much we got, there'd be a slight problem. If we just did this with the test tube open to the air, the gas that we collect would mix with the air and be really hard to measure. So instead what we do is we generate that gas and send it through a tube into a container of water. And when we do that, we can put a little container over top to trap the gas that will bubble up into the water vapor region. This is a process called collecting a gas over water. And so in this gas section here, we'll accumulate all the gas that was generated from our reaction, but also there's a slight amount of the water molecules that are liquids here that evaporate. It depends on the temperature how much. At low temperatures, not very much evaporates, but at higher temperatures, a lot of it has evaporated. And so not only is there the oxygen gas generated by this reaction, but there's also water vapor in there. So this is a situation where Dalton's law would apply because there's two different gases mixed together, and we want to know the pressure of just one of them. So what we've done is we've filled that container with water, we've bubbled the gas through the water as it's formed, and we've collected it into the container. So here's a visual of what's inside that container. We have oxygen gas that was generated by heating up our potassium chlorate, and then we have hydrogen gas, then we have water molecules that have been present because of the fact that they're being collected over water. And here are some of the vapor pressures. As I mentioned, at very low temperatures, you see that the vapor pressure of water is very low. Very little of the water has evaporated. Whereas at the boiling point at high temperatures, a lot of vapor pressure, a lot of the water has evaporated, creating a very high vapor pressure. So I will give you numbers like this. I might say this reaction's occurring at 20 degrees Celsius. And based on, either I'd give you the number or you could read a chart and find that the partial pressure would be 17.5. Okay, here's one final example of Dalton's law before we move on. A gas is collected over water at a temperature of 35 degrees Celsius when the barometric pressure, that means the atmospheric pressure, is 742.0 torr. What is the partial pressure of the dry gas, so the gas that we're collecting without other stuff in it, if the water vapor pressure is 42.2 torr at 35 degrees Celsius. Okay, so here's what we know. We know that the total pressure in the bottle is equal to the barometric pressure, the air pressure, because you can assume that if no water is going into or out of this container, that the pressure outside equals the pressure inside. So we can assume that the total pressure is the barometric pressure, and that our partial pressures inside include water vapor, which is this amount, and the unknown gas, which we're going to solve for. So we know that the total pressure is 742.2, partial pressure of water is 42.2. Set up your equation, plug in your numbers, and you end up with 699.8 torr. Now, something kind of tricky about sig figs here is that we are just adding and subtracting. So remember from our first unit that if you're adding and subtracting, sig figs are based only on decimal places. Since both of these numbers are exact to the tenths place, our final answer stays rounded to the tenths place. It's not based on sig figs. It's not based on the fact that this has 3 sig figs. Okay, on to our second gas law. This is Graham's law. There's a striking picture of Graham. He talked about 2 different processes. The first is diffusion. Diffusion is the gradual mixing of gas molecules. So like if you were standing in one corner of the room and you sprayed the bottle of perfume, those perfume gas molecules, the volatile compounds in there that have evaporated, would travel across the room until they reach the other side. And that process is called diffusion. Now, Graham's law also applies to a situation called effusion. Effusion is a little bit different, even though it's very similar. In effusion, the gas molecules move through a small hole in a container. This is like if you drive over a nail with your car and you have a hole in your tire that's very slowly leaking air particles. The air particles coming out of that hole around the nail are effusing because they are going through a small hole in the container. Okay, so it's a slight difference, but just so you know, there is a difference between those 2 words. Okay, here's what Graham's law talks about. He's comparing effusion rates or diffusion rates, either one. But here's an example of how this would work. If you had a big balloon filled with helium, it's going to deflate a lot faster than an air-filled balloon at the same temperature. And you may have seen this with like buying helium balloons versus blowing up balloons by mouth. You see that those helium balloons start to lose air right away. Well, why does this happen? Graham is able to explain this because we know that helium atoms weigh a lot less. On the periodic table, helium weighs about 4, whereas oxygen weighs about 16 and nitrogen weighs about 14. Now, and remember, nitrogen is N2 and oxygen is O2. So the air is made of oxygen and nitrogen, which weigh about 32 or 28, so about 30 grams per mole, whereas helium only weighs 4, so it's a lot lighter and it's a lot smaller. So those molecules are able to move faster. The helium molecules can move faster through the air than the oxygen and nitrogen molecules in the air. So here's a summary of Graham's law. He said that gases that have lower molar masses diffuse and effuse faster than gases with higher molar masses. So it's kind of like, this is a good analogy, it's kind of like a cross-country runner trying to skateboard versus a big fat sumo wrestler. Who's going to travel faster on that skateboard as long as they're going like on a flat plane? We're not talking about going down a mountain. We're just saying, if they're trying to skateboard, the sumo wrestler is going to go much slower because he's big, fat, and heavy. Here's the equation for Graham's law. What he's going to do with his law is compare two different gases, gas A and gas B, and look at the relative rate. So how does the rate of A compare the rate of B? Well, it's going to be equal to the square root of the molar mass of B, substance B, divided by the molar mass of substance A. Notice that B and A are catty-corner to each other. So this equation is going to show us how gas A and gas B's rate or speed compares. And just as a hint, if you make A the lighter and faster gas all the time, your numbers are going to come out a lot easier. So just remember, A is lighter and faster. Okay, here's a practice problem. Let's determine the relative rate of diffusion for krypton and bromine. Okay, so on your periodic table, find krypton and bromine. Which one has a lighter molar mass? Let's see. Krypton has a molar mass of 83.8, so that's going to be a lot lighter. Krypton is 83.8. Bromine is 159.8. So bromine's a lot heavier, krypton's a lot lighter. Again, you can round these to the nearest whole number as long as your teacher says that's okay. To make your calculations easier, I'm going to keep the whole numbers for now just because it's more exact. So since krypton is lighter, let's make that gas A, and bromine will be gas B. And we want to compare their rates, so we're going to say, let's compare the rate of krypton to the rate of bromine. We'll plug in their molar masses to our equation. So 159.8 divided by 83.8, and then take the square root of that number, and you should get 1.38. What does that mean? Well, that means that krypton goes at a rate that's 1.38 times faster than the rate of bromine. Okay, let's try another one. An unknown gas diffuses 4 times faster than oxygen. Find its molar mass. So this time we don't know the other gas. We know that oxygen. So which one is faster? That's the first question you want to ask yourself. Well, let's see. The unknown gas is faster than oxygen. So let's make that gas A. And oxygen is slower, so let's make that gas B. And we know that the unknown gas, gas A, is 4 times faster than gas B. So you could think of that as 4 over 1. So let's call the unknown A. The rate of A as compared to the rate of oxygen is 4. And we know that the molar mass of oxygen is 32. Now how do we know that? Well, because it's a Hofbrinkel, it's one of those diatomics, it's O2. So 32, we don't know the molar mass of A. Now this is tricky if we're solving for the molar mass of A, if that is our x, our variable. Notice that we have a square root here. So how do we get rid of that? We just square both sides of the equation. So make sure you square the 4 as well as the right side to get rid of the square root sign. So 16 equals 32 over the molar mass. Then you can cross multiply, manipulate the equation to solve for the molar mass, and you get 32 divided by 16, which turns out to be 2 grams per mole. Is that a reasonable molar mass? Well, yeah. The unknown gas is faster, so it should be lighter than oxygen, and it's greater than 1, so it's more than hydrogen's mass, so it's a realistic mass. This gas probably is H2 because its molar mass is 2 grams per mole. Okay, folks, let's see if you are done for today. Can you list the equation for Dalton's law? Could you solve a Dalton's law problem? Can you explain the difference between effusion and diffusion? And can you list the equation and solve a problem using Graham's law? If so, you are done for tonight. Happy effusing!